Hi, I'm Karen McPherson, and this is part of a series of videos I've done on algebraic procedures in need of a conceptual makeover. Some background on why I started this series is because I work with teachers a lot on developing conceptual understanding and leading to procedural skill and fluency. For conceptual understanding, a lot of our lessons do initial exploration and lots of discussion with students sharing their strategies. And procedural skill and fluency is to generalize methods as tools. But how do we get from one to the other? Is developing students' informal reasoning strategies. This series of videos looks at different algebraic procedures and takes the conceptual makeover approach. And how do we develop the students' informal reasoning strategies? Let's get started. Let's take a look at solving exponential equations using logarithms. We'll begin by looking at the equation 5 times 2 to the x equals 240. A traditional procedure for solving this might begin with isolating the exponential part of the expression, dividing both sides by 5. Next, we convert the equation to logarithmic form. Log base 2 of 48 equals x. We'll use the change of base rule, since 48 is not a rational power of 2, and then evaluate the expression using a calculator, giving us an approximate solution of 5.585. For students to use this traditional procedure, there has to be an understanding of what it means to be logarithmic form, and they also need to be able to use the change of base rule. We're going to do a conceptual makeover and approach this in a little bit different way. Before we get started, there are a couple of things that students should have prior understandings of, and that is the idea that writing an expression into equivalent forms will reveal properties of the quantity it represents. We'll definitely be using equivalent forms and some substitution to help us solve equations using logarithms. The second one is a power to a power property for exponents. Students need to understand that if you have an exponential expression raised to a power, that you can actually multiply those two exponents together. All right, let's get started. The first thing that I ask students to do is to express numbers as a power of 10. In some of the cases I'm going to give them, they'll be able to find exact values for the required exponents, and others might require some calculator exploration. I want to be clear that the calculator in this case is not to be used logarithms. That's not the expectation. I want students to do trial and error. Think about 10 to whatever power will give you the number that you're looking for. We begin with these three numbers, and students quickly come to the conclusion that they can write these as 10 squared, 10 cubed, and 10 to the fourth. I use these three numbers to get students to think about multiples of 10. Now the next three numbers require a little bit more thought, and they grab their calculator and start trying some different values for exponents. It gives us an opportunity to think about a strategy. If we know 10 to the 0 gives us 1, and 10 to the 1 gives us 10, then 10 to some unknown value gives us 2. That value will have to be between 0 and 1. Students begin trying decimal values, and they quickly come to what the three numbers could be for 2, 500, and 4,782. I use these three numbers to show that exponents can be non-integer exponents. The next three numbers give us an opportunity to discuss how to get values that are less than 1. Let's talk about h for just a moment. Students will often give me this as an answer, and this gives us a chance to discuss the requirement that it must be written as a power of 10, not a power of negative 10. So this doesn't meet the requirement. As students work on these three problems, they come to the conclusion that exponents can be negative, and that we cannot write a negative number as a power of 10. The last three numbers that I provide students is for them to think about the relationship, the 3.45, the 34.5, and the 345. They used their calculator and they come up with these values, but then we begin talking about how 3.45 multiplied by 10 will actually give us 34.5. And if we use our rules of exponents, we can see why the exponent would be 1.54. Like bases, add your exponents. We can do the same thing with the 345, thinking about that being 3.45 times 10 squared, then using our rules of exponents, we can see that if we add those, we get 2.54. This is a nice extension for students and a great way to think about the exponents and powers of 10. So students now have an understanding that we can rewrite numbers as power of 10. But why might you want to do that? We begin looking at how we can solve equations using that idea. Now, students typically go straight to the x has to equal 2. What I want them to begin thinking about is how rewriting 100 would help us find that x equals 2. So in this case, both of the expressions have the exact same structure, had the exact same base, so we are going to conclude that x equals 2. This is the key idea that we'll be using. Rewriting values as base 10, then using its structure to determine what the exponent must be. Now, let's look at a problem in which the value is not a multiple of 10. Let's look at E. 10 to the 2x. Now, in the earlier exercise, students estimated that the exponent for 500 would be 10 to the 2.7. Using that approximation, we can conclude that 2x has to equal 2.7. Both expressions have the same structure, they have like bases, so the exponents must be the same. We can now solve this to show that x is approximately equal to 1.35. Again, this becomes the critical piece. We've got to be able to rewrite a value as a base 10. Then we can use the structure and the like bases to conclude that the exponents must be equivalent. All right, so we can rewrite numbers as a power of 10, and then we can use that to solve equations. But now we've really got to think about that rewriting piece. I'm reminded of Dan Meyer's talk on headaches and aspirin. And our headache in this case is that we need to rewrite numbers as base 10. And our strategy is right now just doing trial and error on our calculator with a little bit of number sense thrown in. But there is an aspirin for this headache. Mathematicians came up with logarithms. Logarithms will help us find the exponent for a given base to help us rewrite numbers in that form. Let's take a look at a logarithmic form. I give students this expression and ask them about what they see, what they notice, what do they wonder about, and we have a discussion. I answer their questions as we go. One of the key things that comes out in most of the discussions is that B is what we're looking for. We're trying to rewrite numbers as a base 10, and we're looking for the exponent. Well, B is the exponent. So students conclude that a logarithm is the exponent. And that's one of the big ideas that we really want to work with, is that the logarithm is an exponent for a given base. I do introduce to students that because base 10 is a common base, that sometimes they will see it written without that 10. But once students have this understanding about logarithm as an exponent, we're now going to test out that understanding to see if they can apply it. So I give them these 6 problems to work with. Well, they look at A and they hesitate, and then we're talking again that the logarithm is the exponent for the given base, and they come to the conclusion, oh, well, the exponent's 2.5. Rewriting B so that we can see the exponent, we see that that has to be 2. And even if we go on to E, that 500 again, if we rewrite it as a base 10 using our approximate value, then we can see that it would be equivalent to 2.7. F is not possible. And so the idea of bringing back up that we're not going to find the logarithm of a negative value. We understand that we can rewrite numbers as a power of 10. We see how we can use that to solve equations. We now build an understanding that logarithms are a way of determining the exponent for a given base. So can we use logarithms to solve equations? So we look at a, 10 to the x equals 15, and our strategy is to rewrite the number knowing that log 15 will be the exponent for base 10. We now know that x is log 15. So let's take a look when our base is not 10. Let's take a look at D. So what we're going to do is we're actually going to rewrite both numbers as base 10. So we have log 10 log of 3 to the x power equals 10 log 729. Now this is an exponential expression raised to a power, so we're going to use power to the power rule to rewrite this as x log 3 equals 10 log 729. Same structure, same base, exponents must be equivalent. And now we can solve by dividing. And we could use our calculator to come up with an approximate solution. So this procedure with a conceptual makeover, let's look again at that very first problem. Solving 5 times 2 to the x power equals 240. We're going to begin the same way. Isolate the exponential part of the expression. Divide both sides by 5. But the next step is to rewrite each expression into a common base. Now that they have the same structure and the same base, we'll conclude that the exponents must be equivalent. We'll use algebraic procedures to solve for x, showing that x is the log of 48 divided by log 2. And then evaluating the expression using the calculator, we get an approximate solution of 5.585. When we compare the two procedures, we see that the traditional procedure relies on students being able to rewrite it into logarithmic form, whereas the procedure with the conceptual makeover is understanding what a logarithm gives us, and that is the exponent. We also see in the traditional procedure a need for the change of base rule, but the procedure with the conceptual makeover is to just think about algebraically how would we solve for x. Now students will eventually generalize even more, and they'll get to the change of base rule and see that with repeated reasoning they are expressing that the same way over and over again. But to begin with, we're just working with this idea of what is a logarithm, and then how can we use our prior knowledge to help us solve these exponential equations. I hope this has helped and inspired you, and thanks for watching. Have a great day.